Hey, it's recording. Good, yeah, it's recording. So today's date, 10/17/19. Okay, here's our objective today. We want to talk about exponential functions. Okay, and exponential functions are in the form of y equals some a, b to the x. So they're called exponential functions because the x is in the exponent. Does that make sense? That's why they're called exponential. What we saw in my example is that exponential functions get big really fast, right? So when you hear the term growing exponentially, because they'll say that in the news sometimes, they'll talk about growing exponentially, it means that they're growing in that case. And yes, world population is growing exponentially. It really is. So if you want to define the number e is this. The number e, it can be defined as 1 plus 1 over infinity to the infinity power, okay? Now you can't get to infinity, so in calculus, I know this is not calculus, they write it like this in calculus. They go LIM. It's the limit as n approaches this little arrow, infinity, of 1 plus 1 over n to the n power. Okay, and this is the way we'll define it in calculus, but it's not that hard, okay? It's not really that hard to understand. The limit means you're getting closer and closer and closer. The word limit means you're going to get as close as you can get, but you can't get there. So this is a calculus term, and as it gets closer and closer to infinity, you get closer and closer to the number e. John, have you seen limits, haven't you? Yeah.
John.
Okay, now, graph y equals e to the x. Okay, now we know this, that anything, ready, e to the 0 power, it doesn't matter what it is, anything to the 0 power is always 1. Always. Anything, even e to the 0 power is 1. Okay, so that's one number we can get. So e to the 0 power is 1. So I know on this 1, 2, 3, 4, 5, I might even need to get bigger, okay, because e to the 4th, let's see, e to the 1 is 2.7. E to the 2, I'm just using my calculator. What is e to the 2? If I go e to the 2 is about 7.4. E to the 3, I just use my calculator. E to the 3 power is about 20. And then e to the 4th power, if I go e to the 4th power, I get about a 54.6. So I'm probably going to have to go by tens, 10, 20, 30, 40, 50. And so to do a decent job of graphing this, which this isn't hard, I can do this, decent job of graphing this, 1 is about here, and e to the 1 is about 2.7, e to the 2 is about 7.4, e to the 3 is about 20, e to the 4th is about 54. Okay, now, we know the general shape should look like this. And Lily already helped us out a little bit by telling us that this will never be negative, right? And not only that, it will never be 0. So we know when we take a look at the graph, we have a horizontal asymptote at y equals 0. That's my horizontal asymptote. Okay? Not that bad, right? All of these exponential functions will always have this shape. It's kind of like a J. Does that look like a J? All of these exponential functions will always have this shape. Okay? Now, domain and range. Well, domain is forever wide, right? And not only that, we can plug in any number. So the domain is simply x equals all real numbers. Forever wide, right? Now the range, though, let's go back to what Lily said. The range,
It's always going up, though.
it's always going up. The range is never 0 or negative, right? Does that make sense? So the range is not down here at all. The range has to be y is greater than 0. Not equal to 0, because you can never, remember half of the half, you can never get to the door. Does that make sense? It'll never get to 0, so the range is simply going to be y is greater than 0, and the domain is forever y, right? Even though it's going up, it's always moving over, okay? Make sense? Now, on example Number 2, we've got the exact same graph, but we're going to take everything down 2. So we're going to take it down 2 units, and it's going to be 3 times as tall. Well, that's going to be a little tough to see, but I'm just going to try and draw it a little steeper, okay? As long as we get the general shape, okay? So I've got my 10, my 20, my 30, my 40. And let's take this whole entire graph down 2. So I'm going to put a horizontal asymptote down here at -2. Okay, so my graph, just taking my graph, and I'm just going to bring it down 2, okay? So my horizontal asymptote now is at y equals -2. It's going to go through at -1, and it's going to be just steeper. So the difference is when I graph this one in, and I won't do a perfect job, I could, but I just want to make sure it looks steeper. 3 times as steep as the last one. Do you see the comparison? The second graph is 3 times as steep. The asymptote has been moved down to -2, and the beginning point of 1 goes down to -1. I just brought it down to, okay? Domain and range? Well, domain is easy. How wide is this graph? Domain's easy. Domain is x equals all real numbers. And the range, it doesn't quite hit -2, does it? But from -2 it goes up. Y is greater than or equal to -2. Okay?
On the left side, you wrote down to something, and I don't know what that is.
Greater than, my bad. Here. Where you at? Down 2 units, yeah. And that's no equals on that, my bad. Okay, so let's go back to what I have, okay? Here's the parent function. Here's my e to the x. It is a growth because e is about 2.7, so it has to grow. Okay, the base is 2.7, so it's got to grow. Domain is all real numbers. It never touches 0, so it has to be an asymptote here, okay? Then what we did on the second example is we just merely took it down. We just took it down 2 units. So the asymptote went down to -2.
Why is
The
it
point at 1 went down 1, 1, 2, so the x-intercept, sorry, the y-intercept is at -1. Julia?
Yes.
Asymptote.
Is that just
Yes,
is that
why?
just like the definition of when something never hits 0?
Yeah, an asymptote was a line, a boundary line. How's that? And you can have vertical asymptotes too, Julia, which we'll talk about in the next chapter, okay? So all an asymptote is an invisible boundary line. Does that make sense?
Why? Why is it y is greater than or equal to?
It's not. It's supposed to be just greater than.
Why?
It never touches this line. It never okay, let's go back to this. As this is like half of a half, half of a half of a half, half of a half of a half, half of a half of a half of a half.
Yeah.
Will it ever reach 0? No. And that's why it's got to be greater than 0, but not equal to 0.
If it's graphed a certain way, like 3dx, and then -2.
Right. So then
So
I
it's same.
took this down, took the entire graph and brought
Disease
it down 2 units.
Yeah,
Are you with me?
I get that. I get that.
Okay,
So
now, let's,
whatever-
yeah.
Like the starting point or the intercept for these kind of things they're called like you would think of it as that, but they never actually go through.
Never actually go through. No. It's like an invisible boundary line that keeps it from going
So it's
there.
really on like 1.9 something.
It will go to 1.9. Yeah, it will hit -1.9. It'll hit -1.99. It'll hit -1.99999, but it'll never reach -2. Just like here, it'll hit 0.1, it'll hit 0.001, it'll hit 0.00001, but it'll never hit 0. Seth?
So is the second graph just the first graph down 2 units?
Hallelujah, exactly right. Yes, with one small exception, if I can add, the 3 here, I just made it steeper. Does that make sense? And to draw it steeper, we could do a T-table and I just need the shape, and I need where it hits, and I need the asymptote. So for me, I need the shape, it's that J shape.
You don't need all the points.
I don't need all the points. I just need the general shape with the asymptote and the y-intercept, okay? Yeah, Austin?
When is E used?
Oh, all the time. I'm not kidding. In biology, seriously, it is used all the time. In biology, it's used in chemistry. Real quick, and I know we're out of time, but this guy's sick, right? So the bacteria in your body or the virus in your body are growing continuously. You with me? And so if I were a biologist or a doctor and I wanted to treat your illness, I would know that your bacteria are growing continuously. So they grow at this rate. Okay?
Okay.
So it's used a lot. And then if I give medicine, and the medicine kicks in and starts working, it's going to start dropping at that rate because the medicine is going to work continuously, right? They don't take coffee breaks. Oh, thank God they don't take coffee breaks. So when you get your medicine, oh man, I'm tired. The medicine says, I'm tired, I'm taking a coffee break. No, they work and pounding on that virus continuously. But then the flip side, sorry Alex, the flip side is that that virus is starting to pound on your body continuously, right? Those cells are growing all the time.
What's the X that was called?
What's the what?
X is
That's all.
Oh yeah. Okay, now number 2. So number 2, what we want to do is this. So let me go ahead and real quickly show you what we got going. Oh, doggone it. So if I graph this on my calculator, I want you to see what it looks like. So you have an idea of what it looks like. If I go my 2 to the e to the x to the negative 0.2x. Okay. Now before I graph it, because this is a negative, this graph's going to go down. Okay, it's going to go down because it's going to be decay. Now let's take a look at it. Okay, so real quickly, if I graph this, okay, it looks like the opposite, doesn't it? Instead of growth, this one's decay because the rate in here is a 0.2. Okay, so I know for sure that it's got to go through 2. Okay, I know that it. And I can use my table to get a decent graph on this. If you remember, go back to my table. And I know at 0, it goes through at 2. If I just use my table, it goes through at 2. So, but then it's going to get smaller and smaller. So if I put 1, 2 here, 3, 4. Again, I don't necessarily need to have a perfect graph. What I want is I want the asymptotes in the right place. I want the shape to be right. And I need to have the y-intercept. These are the 3 things I need, okay? So I know that at 0 it goes through 2. Boom. Has to. Because anything to the 0 power is 1, and 1 times 2 is 2. I know the shape is that it's going down, right? And we don't have to have a perfect graph, but we need the shape, that G shape, okay? That J shape. And I need to also know there's an asymptote right here, okay? So what I have then is my y equals 0 as my horizontal asymptote, okay? Now, what we have is a decay. So let me rewrite this as y equals e to the 1 minus, no, I don't want to write it like that. I want to write it like, I don't want to write it like that. I want to write it the other way around. I want to write it as 0.2. Hold on, give me a second. 0.2, I want to rewrite as 0.8 minus 1, 0.8 minus 1, 1 minus 1.2. I want to write it like this to the x, okay? Actually, let's not do that. That's going to make it too hard. Let's not do that, okay? Because the percentage change is you're dropping, I want you to see that you're dropping 80%. We'll talk about that later, okay? Let me flip the page and talk about that later, okay? All right, 3, this is just like what we did in our book. This is easy. Think about E as like X. Yeah, Autumn?
For the 80%, would you just take like the 100 and then subtract it by the 0.2 and
20%.
what's left as the percentage?
Yep,
Oh.
that's exactly it. Yep. Okay, E to the 10. That's it. E to the 10. What did I do? I just added exponents. That's all I did, right? I'm going to get a 27. Ooh, where'd the 27 come from? Good. E to the 15. Right? I'm going to get a 3 over an E squared. Does that make sense? And then finally, let's go back to our banking formulas, which we should be able to do by now, right? So banking formulas, compounded interest is going to be A of t. So if you didn't get this a half hour ago, hopefully right now you will. Amount over time is equal to P, which we call the principal. It's what you invest, 1 plus r over n to the nt power, where P is what we call the principal. It's how much money we put in the bank. It's our beginning amount. Our R is an interest rate. Yeah. Oftentimes, we have to move the decimal 2 places because we get it as a percentage, right? N is the number of times a year. Number of times a year. So if it's monthly, N is 12. If it's quarterly, N is 4. If it's semi-annually, N is 2. If it's daily, it's 365, okay? And then T, of course, is time in terms of years, okay? T is time in terms of years, okay? Continuous interest is something that's going to grow continuously, okay? They call it the PERT formula. I'll show you why. It's called the PERT formula. A of T is equal to P times E to the RT power. They call it the PERT formula. You can see P-E-R-T, right? PERT. But again, that's your principal. That's what you plug in. The number E, which we found on our calculator. My R, which is my interest rate to the T. Okay, so let's do example 4. Almost done. Okay. Keegan has $4,000 to invest. The first bank will give her 4% compounded quarterly for 5 years. The second bank will give her 4% for 5 years, okay? But continuous interest. So she's got 2 banks. We got Bank A. We've got Bank B, okay? So Bank A, let's see. Bank A is going to give her, the first bank, 4% quarterly for 5 years. So let's figure it out. So Keegan's going to put it in for 5 years, so it's going to be A of 5, or the amount over 5 years, okay? A of 5 means the amount over 5 years is equal to 4,000 times our 1 plus 4% is 0.04, right? Because we're going to move that 1, 2 places. Divided by, we're doing it quarterly, so we're doing it 4 times a year. Good job, Seth. To the 4th power, or I'm sorry, divided by 4, to the 4 times 5. And that's a time sign, okay? And I'll stop and let you catch up, okay? So we just used this formula. Put in 4,000. 1, you got to have the 1. The 1's super important because you want your original money back, right? R is the interest rate. I changed 0.04. 4%, put in 4. Quarterly, there's my 4 to the 4 times 5, because that's the one. And I just use my calculator. That's all I'm going to do. I'm just going to use my calculator and go, okay, I can do this. It's easy. I'm going to go 4,000. 1 plus 0.04 divided by 4 to the power of 20, right? 4 times 5, 20. So Keegan now has $4,880.76 in her bank account. So she made about $800, right? 880 is what she made. Okay, cool. Now Bank B is going to give it to her continuously. Better deal, right? So she's going to use the other formula. So we're going to go A of 5 amount over 5 years is equal to my 4,000 E to the 0.04 times 5. And again, just going to use my calculator. And I've got an E button on my calculator. It's E button is right over here. Right, it's over here. So I'm going to go, all right, I'm going to go 4,000. And I go E to the 0.04 times 5. And I can answer about $4,885.61. Okay? Right? So she made about $5 more, okay? Now, real quick,
Continuous interest.
that's on continuous interest. So she made about $5 more. Not that big of a deal, right? She made about $5 more. Okay, now here's what I, real quickly, and this is not a political statement, this is just a fact. If you had a lot of money, if you had a lot of money, right? You're one of the 1%, right? This is why you can always stay rich and the rest of us stay poor, okay? This is true. It's just basic math. It's not political. Basic math. If you had 4 million, right? If you had 4 million, then you didn't just make $5 more. You made $5,000 more. Right? If you had 4 billion, wow, the amount of money you can make, right? So it's kind of depressing for the rest of us, but anyway, that's just the way